Alright, in this video we study the complex Fourier series that is of this form. So the index varies from negative infinity to positive infinity, and the coefficients are complex numbers in general. And here we have exponential of I, k, x, where I is the imaginary unit, of course, and x is a real variable. So let's start. First of all, let's compare this with the real Fourier series of this form, which we have been studying so far. Ak cosine kx and bk sine kx. So apart from being complex valued, this complex Fourier series is actually equivalent to this real complex series. Well, except for the coefficients being real or complex. That's because of this Euler's formula. As you know it, exponential of I kx, where k and x are real. This can be written as cosine of kx and I sine kx. So if you substitute this into this series, then you have something like this one by changing coefficients appropriately. Now, suppose we have a function f that belongs to r2 pi and 1. So that is a periodic function with period of 2 pi that is absolutely integrable. In this case, the complex Fourier coefficient ck is defined as 1 over 2 pi integral from negative pi and pi. So this can be 0 to 2 pi, but it's just a periodic function, so this is okay. And f of x, an exponential of negative I kx and dx. So this is not this negative sign. So rather than this positive exponent, we have negative exponent here. And so if we determine the coefficients in this way, then the complex Fourier series of this function f is this one. So let's write it as s of f, that is this sum, ck and exponential of I kx. So this ck is this ckx, okay? So this one is this one. Okay, next, let's forget about this. So in this case, in the previous case, we assumed that there exists a function f. And for this function, we determine the complex Fourier coefficients, okay? But now forget about this, and suppose a function is defined by this complex Fourier series. Eikx. And assume this belongs to r2 pi 1. And now let's multiply both sides by exponential of negative I m x, for example. So multiply both sides by this. Then on the left hand side, we have f of x exponential of negative I m x. And on the right hand side, we have this summation, ck exponential of I k minus m x. And let's integrate both sides from negative pi to pi. Negative pi to pi. Okay. Now on the right hand side, this function is since we're assuming that this is absolutely integrable, we can apply Algel's theorem and swap the order of integral and the sum. So we can put this coefficient out, and exponential of I k minus m x dx. So what is this integral? We consider two separate cases. So case 1, when k is equal to m, then this integral becomes just, so this exponent becomes 0, so it's just 1 dx. That is 2 pi. And second case, when k is not equal to m, then in this case we have this integral I k minus m x dx. So we can just treat I k minus m as a constant. So it's I 1 over I k minus m. No, this is not 0, so it's okay to divide by this. And this k minus m x and negative pi. So this is equal to exponential of I k minus m pi minus I minus k minus m pi, which is equal to 0. So this one corresponds to, on the complex plane, so pi times integer, some integer, so k minus m is an integer. So we rotate this point 1 time, 2 times, 3 times, and so on by pi. So k minus m times in the counterclockwise. Okay, here we do the same thing but clockwise. But in either case, we always get the same number here on the complex plane. So this should be equal to 0. So let's go back to this integral. So this is equal to 2 pi if k is equal to m. Okay, and otherwise it's 0. So the only term that remains is when k is equal to m, so that it's cm. Okay, so this is the result. And as you can see, if you divide both sides by 2 pi, then we have the Fourier coefficient of this function that we defined here. Okay, let's consider an example. F of x equal to exponential of I x over 2 for x between negative pi and pi. And we're assuming this is a periodic function with a period of 2 pi. Okay, and so this looks like this. So if you consider the real part, that is cosine of x over 2, and the imaginary part is sine x over 2. So if you plot x versus this function, the real part is this one, cosine. So when x is equal to 0, that's 1. And when x is equal to, let's see, 2 pi, x is equal to pi, then it should be 0. Okay, let's see, this is pi, and it looks like this. And negative pi looks like this. Okay, and so this continues repeatedly. So we just copy this function to this range, like this, and like this, and so on. So this is the real part. And the imaginary part is sine x over 2, and when x is equal to 0, that's 0. And when x is equal to pi, that is this. So it should look like this, like this. So if you repeat this, so if you shift this by 2 pi, you get something like this. And like this. So as you can see, the real part is continuous, but the imaginary part is not continuous. And let's calculate the Fourier coefficients. Ck, let's multiply by 2 pi, just for the sake of simplicity. And cosine, not cosine, it's exponential I x over 2 times exponential of negative I kx dx. So that is exponential of I x 1 over 2 minus k dx. And that is, what is it? 1 over I, 1 over 2 minus k, and exponential of I x 1 over 2k negative pi and pi. And that is exponential of I pi minus negative I pi, this. And let's split this into, so I pi 1/2 times negative I k pi. And here we have I minus pi half times I plus plus I k pi. Okay, so this one, I pi half is equal to, that is I. And I negative, this one, I negative I pi half is equal to negative I. And exponential of negative I k pi is equal to, what is it? It's pi, so negative 1. And if k is odd, then it's negative 1. If k is even, it's positive 1. So it's negative I to the power of k. And this is actually equal to this one too. So substitute these values into here. We have 2 pi ck equal to 1 over I 1 over 2 minus k. And let's see, I. And this minus and negative I. And this. So these negative signs cancel, and we have, so this I, they cancel, and we have 2, this, and 1 over 2 minus k. And let's see, so let's multiply both here and here by 2. We have 4 minus 2k. So ck is this divided by 2 pi. We have 2 k and pi 1 minus 2k. So this is the Fourier coefficient. It's real. So after all, we have the Fourier series of this function as this 2 over pi and sum over k from negative infinity to positive infinity, and negative 1 to the power of k, 1 minus 2k, and exponential of ikx. Okay, next let's consider this partial complex Fourier series. K varying from negative n to positive n, and ck exponential of ikx. And use the Euler's formula to expand this exponential function into cosine and sine. And then we have this C0. So when k is equal to 0, we have just C0 because this is 1. And k from 1 to n. And so positive k and negative k, let's combine them together. And we have ck plus c minus k and cosine kx. And the imaginary part, we have I and ck minus c minus k, and sine minus sine kx, because sine function is an odd function, so we have this negative sign here. And so if we define 1/2 a0 to be c0 and ak to be ck plus c minus k, and bk to be I ck minus c minus k. Then we have this partial series as 1/2 a0 and from 1 to n, and ak cosine of kx and bk and sine of kx. So if we take the limit, assuming this converges, then we have the real Fourier series. So assuming this and this are all these coefficients ak and bk are real. Okay, so that can happen if these are complex conjugate of each other. Okay, so this is purely real, and this will be purely imaginary. So multiplying by I, it becomes real. So basically, the complex Fourier series and real Fourier series, they are equivalent. Since the real and complex Fourier series are equivalent to each other, we can apply all the theorems that we have proved for the real Fourier series to the complex Fourier series. So I will list those theorems without proof, because the proof is essentially the same as the previous one for the real Fourier series. So first one, lemma, that is zero function. So assume the function is periodic and absolutely integrable. Then if the complex Fourier coefficient of that function is 0, negative ikx dx. If this is 0, then for all integers, of course, then f of x0 is equal to 0, where x0 is a continuous point. Continuous point means the point at which the function is continuous. Okay, and naturally, if f is a continuous function, then the function f is identically equal to 0, if this is true. And next theorem, if the complex Fourier series of f converges uniformly, uniformly, then we have f equal to s of f. So the function f is equal to its complex Fourier series. So this is just like we have seen for the real Fourier series. And to see if the complex Fourier series converges uniformly or not, the following theorem is useful. So if we have a Fourier series such as this one, ikx, then if the series of the coefficient converges absolutely, then this Fourier series converges uniformly. So if this ck converges, so this means the coefficient converges absolutely, then this Fourier series converges absolutely. Uniformly. And just this is also just like the one we have proved for the real Fourier series. Okay, that's all for this video. See you later.